Hello, this is Paul from Foresight Tech. In this video, we are going to deal with the derivatives of logarithmic functions. Let's see the material. First, I will introduce the derivative formulas and then give a proof as well. Then we will practice 3 questions together about how to use the derivative formulas. And first here is the derivative formula for logarithmic functions, right? So the first formula is a general formula with the a as a base. And the second is a natural logarithmic formula, right? Natural logarithmic functions. And we can see the formula is much easier than the first. You know, that's one of the reasons why we like the natural logarithmic function. And we were going to prove the first general formula, okay? And if we have the first general, of course, and the natural logarithmic is just a special case, which means if we take Ka equals E, and then we will get the second formula. Okay, that's going to see. And all we need to do for this, right, is so I will going to write the special case, which means a equals 1, right? So I will going to just take a equals 1. And then we look at ln at a should be equals to ln at e, which is 1. Can you see? And therefore, the first ln a we don't have. And so the derivative just goes to reciprocal function, right? And that's why the second formula works. Okay, so if we prove the first, then we're going to prove the first later. Okay, so first we're going to look at 2 very simple examples, how to use the first or the second formulas. Log 5 at x, which means we have to use the general formula of the first one, right? A, the base a equals 5. Therefore, we have 1 over x times ln at 5. Okay, so easy to get. It's very easy to get the first one. Let me show you the answer here. Or should we do this? Okay, do fraction, okay, which is 1 over x times ln at a. A is 5. So this is the first. The same we're going to the second. The second is still a general. Okay, we call the common logarithm, right? Which means the base a equals 10. Let me write that first. So we can go to C, which means log 10 at x, right? Okay, this is a common logarithmic. And then, of course, in this case, a is 10. Okay, so we're going to write the answer directly. So what do we have? We have this. Okay, so it's 1 over x over l times ln at 10 because a equals 10. You can see it's super easy to get it. This is the first 2 simplistic example. Okay, now we will move to prove the first general formula. Okay, we will not use the definite, okay, the limit definition of the derivatives. That's too complicated. What we are going to do, can you see? We will use the implicit differentiation we just learned from the last topic. Okay, this is a very, very important tool for us. Okay, all we need to do, the original function is a logarithm, right? And the inverse function we know is the exponential functions. Okay, the base a raised to the power of the logarithm equals x. Okay, so all we need to do is deal with this equivalent form equation. Of course, we call the implicit equation, right? From this implicit equation, we are going to find the derivative of y to x, because we know the derivative of the exponential functions we learned before. How to do? Of course, we know how to do is this. Let me show here. Is implicit differentiation, which means we need to take a derivative, okay, to both of sides of this equation, right? All we say is differentiate. We're going to see, as we call it, differentiate both sides, right? This is the common way. After we differentiate both sides and resolve for dy dx. Okay, let me see here. So the first take a derivative, the second, the right side take a derivative. Okay, the right side is 1, easy. How about the left side? The left side is a composite function. Why? Because the power y is a function of x, which means y is the inner function. Therefore, the outer function is exponential. It's super easy. And what does it mean? It's chain rule, right? We have to use the chain rule. Let me just put here. So you will see now. This should be the chain rule we have to use. Okay. We just explore the outer is exponential. Therefore, the derivative of the outer function is the first, right? A raised to the y's power times ln at a. Okay, so what is the inner, which is the derivative of y to x? Because the inner function is y. Does that make sense? Okay, so we get the left, the right. We have this equation. Now, all we need to do is solve for dy dx. Super easy, okay? That's a linear equation. And directly get 1 over a y ln a. So good. But we need to back us up to do that. What is y? Okay, y is that, but we know ay is what? Ay is x. Therefore, I just plug it here. Okay, easy to get this. Because ay equals x, right? Can you see from the beginning? Ay equals x. A raised to the y's power equals x. Therefore, ay equals x. Plug it. This is already the answer. Have you seen? It's super easy, right? If we use the implicit differentiation, okay, it's very easy to find the derivative of a logarithmic function. So that's good. This is the proof. Now we will move to 3 questions together, okay? Let me see the first question. So here. And look, we have a complicated function to take a derivative. But you know this function, if you break it down, is a composite function, right? The inner is here, the inside, which is a sine square. The outer is ln at u, as a natural logarithmic function, right? Okay, so we have all the formulas, so it should be not difficult. Whatever the rule we have to use first is chain rule, right? Because there's a composite function. Okay, so let me write directly. We're going to do this, and f take prime equals this. Of course, we have 2 parts, right? So the derivative of the outer times derivative of the inner. Let me find out the derivative of the outer function. We just say is ln at u, right? Okay, so all we need to do, see, this is the derivative, this is the outer function. We're going to take a derivative. We just learned this natural logarithmic function. And therefore, we have this. Okay, so we have the derivative is a 1 over reciprocal function, right? 1 over u. And then I'll plug this to the first part. What do we get? We will get this, okay? We will get a fraction. Of course, the first fraction is 1 over u. And the u is what? U is sine square. So I just directly plug sine square x here. See, this is 1 out of u. The derivative of the outer times the derivative of the inner. I wrote one more step. What is the inner function is sine square at x. Okay, so this take a derivative. So here is just the chain rule. Okay, so all we need to do is take a derivative to the second part. Easy. Okay, so let me copy the first. Okay, I'll copy the first is a fraction. It's just a symbol, okay, to copy. So I see this is a 1 over sine square x, okay, times, what is the second? I have to use chain rule again, okay. Why? Because this is a composite function, and the inner is sine x, so the outer is u square, power function. Okay, so let me write here. We have to use chain rule again in this step. Okay, what the chain rule? Okay, is the outer times the inner, right? The derivative of the outer, derivative of the inner. And the outer function is u squared, which means 2 times u. What is u? Sine x. This is the derivative of the outer times derivative of the inner, which is cosine x y. Because the inner function is sine x. Sine x take a derivative, we get a cosine x. Can you see? That's all. Okay. Now what we left is just a simplify. It's simple. We just going to simplify and see what I get. I will get this fraction again. Okay. And let me write the fraction, which is this. What we left on the top after we simplify. Let me show. No. Let me show first. Okay, sorry. Let me show first. We're going to simplify, which is sine x on the top. Can you see? And sine x on the bottom. So we cancel, divided out the 1 sine x. So what we left on the top? The top is 2 cosine x. What we left on the bottom is sine x. Okay, now and we don't need to stop at here because cosine x over sine x, the quotient rule tell us is cotangent x, right? Okay, I wrote down the final should be like this: is 2 times cotangent x. Okay, so it's already very simple. This is the answer for the first question. And we look at it, it's not difficult. All we need is the derivative formula of the logarithmic, right? And including the chain rule. The one more question, so let's go into here. Let's go into these questions. Looks very similar. However, we have a log. What is a log? Common logarithmic, which means the base 8 is not e, right, but the 10. So we have to use this time. We have to use the general logarithmic function. Okay. Of course, and the way is very similar. Why? We see the function is a composite function, right? And there is a composite function, so we have to use a chain rule. Okay, I write here is the same step. We need to use a chain rule. Okay, so let me show here first. And what is the derivative? The derivative of f should be like this. Chain rule always do this way. Okay, and the product of two derivatives. Okay, derivative of the outer times the derivative of the inner. What is the outer function? Of course, u is sine x squared. Can we see here? This is u. Therefore, the outer function, or you say the outer side function, is log at u, which means this one. Let me put it here, log at u. This is the outer function. We take a derivative, and equals what? Equals this. Equals the fraction. Remember, this is what? General logarithmic. Why? Because the base is 10 this time. Okay, so what do we have is 1 over u times ln at 10. This is the formula we just learned, right? We plug this to the first. Okay, and then we get the derivative of the outer function. Let me put the fraction there. I just copy, right? All we need to do, I just put here. So the top is 1. Can we see? The bottom is u. What is u? Of course, we can see u is sine square. So I plug sine square to there, and I will directly get the sine square at x, and then times ln at 10. See, this is the derivative of the outer. Okay, one more step. Times the derivative of the inner. I just wrote the one more step. What is the inner function? We just discussed. This is the inner function. Take a derivative. So this is just the chain rule. Now what do I do? And then we can just copy the first, right? Okay, I'll copy the first first. The first term is this. Okay, so 1 over sine square times ln at 10. This is what I copy. So what is the derivative of the second? You know this is also a chain, also a composite function. And the inner function is sine x. The outer function is u square. Okay, so we have to use chain rule again. Let me put here. So we have to use the chain rule again. Okay, so of course you know it's just like this. Is 2 derivative, and the outer function is 2 is u raised to the second power take derivative, which is 2u, right? Let me write here 2. What is u? Sine x. And this is the derivative of the outer, or the derivative of the inner. Okay, sine x take a derivative, which is what? Cosine x. And now can you see this is everything we get. So the same, the last step we're going to simplify, right? We're going to simplify. Okay, see what do we get? We will get this. And we will get a fraction, of course. I will going to write the fraction. Okay, little bit shorter. It's good. No. And then what we left after simplify, I will going to simplify. See, still the same. I divided out by sine x plus up and bottom. So what we left? We left at the top is 2, right? Times cosine x. The bottom we left the sine x times ln at 10. Can you see very similar? Now we have what? We can simplify a little bit. Because sine, cosine over sine is cotangent, right? So what do we have? The final is like this. 2 times cotangent x. The bottom is ln at 10. This is the final answer for this question. Then we have one more question. So let me look at the last questions. And through these questions, we finally get another very important result. In the future, you can directly use. Okay, see, we have this function. This function is strange. We have absolute value, which means that the domain x should be any real number except the 0, right? X could be negative number this time because we have an absolute value here. How about this? Directly going to derivative, we do not have any formula. Okay, so what do? We just break this function down into the piecewise. You know, this is a piecewise function. Okay, so the first step, I do this. I will just break it down. Okay, so I break it down, which means let me see. I will still get this. I will write it into a piecewise function. Therefore, we have fx this. We have 2 cases, okay. And the first, can we look at this? When x greater than 0. The second case, when x less than 0. Okay. When x greater than 0, of course, we just ignore the absolute value, right? So therefore, we have this, which is ln at x. This is the first. The second case, when x is negative, so absolute value of x is negative x. Therefore, the function goes to this. The function goes to ln, add parenthesis, negative x. Does this make sense? So now, we just break it down. We do not have absolute value. Okay, so each function, we know how to take a derivative. Okay, now, we take a derivative piece by piece, one by one. Okay, the first. Let me look at it when this, okay. And when x greater than 0, we're going to take a derivative. So the derivative of f this time is ln, this is the function, right? And parenthesis take a derivative. So what is the answer? Directly, this is the derivative of the natural logarithmic, which is 1 out of x reciprocal, right? Now we're going to the second. Okay, so we do this. When x is less than 0, How about the derivative? Okay, the derivative of f should be equal to this. Let me copy this function first. Okay, so we have this function, right? Take derivative. How about this derivative, this term? And this is a composite function. What do we have to do? We have to use chain rule. Okay, let me write down. So this term is chain rule because this is a composite function. So let me write here is chain rule. Okay, so chain rule is two derivative terms together. What is the outer function? Because the inner you see is negative x. So the outer is ln at u. ln at u take a derivative is what? That's natural logarithmic, which is 1 out of u. Sorry. Is a reciprocal, right? So let me go into write this again. Is a reciprocal 1. No, sorry. It's just to do this. Let me write the fraction. Is this fraction? Can you see this fraction? Let me get this down a little bit. No. Okay. So what the fraction? The fraction is 1 over u. What is u? Is negative x. Right? This is the derivative of the out. Let me times the derivative of the inner. The inner function is negative x. Take a derivative is negative 1. Easy to get. This is a negative 1. Okay, do calculation. It's easy to get what the answer 1 out of x again. Can you see what we get? No matter the first piece or when x is greater than 0, the derivative is reciprocal. When x is less than 0, the derivative is still reciprocal. What kind of a conclusion we can get? So we can get this conclusion. So no matter if x is what, the derivative of fx always equals reciprocal. Let me copy the original function, which is ln absolute value of x. Okay, absolute. This is f, right? Parenthesis. Take a derivative equals a reciprocal function. Can you see? This is the final answer for this question. Of course, we already get all. However, I will show you a little. Okay, so and this final result is very important in the future. Okay, the absolute value of this kind of natural logarithmic and the derivative equals reciprocal. In the future, we are going to use. So let me highlight these results for you. So I can do this highlight. Okay, that is okay. So let me get it. So this is that's the one I was going to highlight for you. So let me put the no. Yes. So now, so I will get this highlight. So in the future, okay, in the future, try to memorize this and directly use the results. That's all for this topic. Thank you. If you have any question about this topic, please leave your comment. If you like this video, please give me a thumbs up, and you are very welcome to subscribe to my channel for more videos. Thank you for your support. In the next video, let's see, we are going to deal with the logarithmic differentiation, which is an important method to find the derivatives of complicated functions. Hope to see you there. Thank you. Have a nice day. Bye.